اشتراك يموت مني في الساعة اللي قبليها.
عنده دلوقتي؟
Is it Arabic? Yeah. Yeah. Huh? No, absolutely not. Don't worry. ما سمعتش. هو سمعت بيقول لك ما تتكلمش فرع عليه. ما ينفعش نتكلم بقى ورا. I English all the time.
You see the red record?
Yeah, record, yeah.
Wait, Kentucky? Is Derby this week? Find your girl. And a horse.
I just want to hear.
He wants a horse.
I just want to
Okay, good morning everyone. Good morning. So we're going old school today. Okay, my iPad has malfunctioned. Some of you kindly offered yours, but I also did not bring my laptop. So I think at least for today and hopefully by Friday, my iPad should be back to normal. I've given it to the OSU ETS people, so let's see how long they take. Until then, here is what I'm going to do. I'm recording a lecture. As you can see, there's a video camera running behind you. Once the lecture is completed, this is right at after 2 o'clock or so in the afternoon, I'll post this lecture video on a YouTube link and send the link to everybody. People who are unable to come, they can take a look at it. And hopefully the problem will be sorted out by Friday. Okay, if not, we will see what to do. All right. So this was the mode of teaching that I usually used to perform, when I was before this iPad business and so on. I've been teaching since 2009, and it's been on the chalkboard every time I've taught mechanics of materials. So for me, it is back to my own roots. Maybe it is different for some of you who have been accustomed to doing things on an iPad or on Zoom. Okay? All right. We're going to start bending stresses, and I'm going to call these as bending stresses and transverse shear stresses, because I'm going to do them all in one fell swoop. But before that, we got some unfinished business in terms of bending moments and shear forces. Okay, so first things first. Can people in the back see my writing clearly? Okay, all of you in any corner of the room, you can all hear me properly too? All right, fantastic. So bending and shear stresses. I want to introduce the formula. We will look at a very brief derivation of this, but I want to introduce a formula to motivate something. Bending stress typically is denoted by sigma. Given by the combination of these three characters, M, Y, and I. I is moment of inertia. We will look at these things slowly as we get there. Y is some distance above or below the centroidal axis. Not very important. The thing that is important to me here is this capital M, which is your bending moment. M. Likewise, transverse shear stresses. You would have seen shear stresses before. Okay, we did the following. So previously, tau average was the shear force by the area. So shear force V by the area. Now this is kind of erroneous. Okay, this is not the real shear stress, because this is just averaged over the entire area of cross section, but in reality shear stress is going to keep changing across the cross section. So we are going to look at a different formula, which is a kind of a correction of this formula. This is like a back of the envelope calculation. This tau is equal to V by A. What we are going to be looking at is something that is more proper. And that formula is called as transverse shear stress, different from this guy. So tau much more scarier looking guy, because there are many elements there which we have not spoken about. What exactly is T? T stands for thickness. Don't worry about it right now. We're going to get there. I stands for moment of inertia. We already have encountered it in torsion, right, when we did the polar moment of inertia. Q, we have not become friends with Q yet. We will hold on for the time being. The thing that I want to mention here is this V, which is your shear force. Okay, so V is shear force. Now, why am I motivating all these things is for the following reason. When materials fail, they will typically fail at values of stresses that are the maximum value. Correct? So, what I would like to do is consider a problem or consider some kind of a physical body and then find out, okay, what is the largest bending stress and where does it occur on this body? What is the largest transverse shear stress and where does this occur on this body? And that's a function of what? That's a function of what the bending moment is. It's a function of what the shear force is. And so it is all likely that the maximum bending stress, sigma, is going to occur where I have the location of the maximum bending moment. If this is high, this is going to be high, obviously, right? You see the direct correlation. Likewise, if my shear force is high, my transverse shear stress is also going to be high. So in any given problem from now on, I need to figure out, hey, what is the largest value of the bending moment? What is the largest value of the shear force? And where on earth does it occur on this body? So that's the motivating reason for what we are going to be doing next. So our aim from now on to obtain M max value, the maximum bending moment value, for a given problem. Because this dictates what the magnitude of the shear stress is going to be, what the magnitude of the bending stress is going to be, so this is directly correlated to sigma max. This guy is directly correlated to tau max. And we do this by drawing what are called as the shear force and the bending moment diagrams. Okay, this is the hallmark of mechanics in many ways. Is if you are a person trained in mechanics, you need to know how to draw the shear force diagram and the bending moment diagram. So we will learn shear force diagram, which I'm going to call as SFD. The shear force diagram will tell me where is the maximum shear force occurring and what is the magnitude of that shear force. It tells me and the location, and then we will also learn to draw the bending moment diagram. Which I'm going to call as BMD. People in the back, can you see if I write it this low here? Okay, thank you. So BMD gives me the M max value and the location along the beam where it occurs. Okay, gives me. foundational things. Okay? Your training as a mechanical engineer or a civil engineer or an aerospace, a structural engineer, environmental engineer is not complete without knowing how to draw these two. And what I want to do within the next few lectures is, just by looking at the problem, we want to be able to just draw these things without doing any calculations. That is the ability that we need to have. Okay, and I want to train us to think that way. I'm going to take off this panel here. And I want to start by looking at a simple example. I'll show you how to construct the shear force in the bending moment diagram. And then I will tell you that, okay, this is laborious. My aim in life is to do things as quickly as possible and take a nap. So, I'm going to teach you something called as the graphical method, which will be a much more elegant, more mathematically compact way of obtaining the shear force in the bending moment curves. Okay? So here is just an example of how to do it manually, laboriously, with very little elegance. The problem. I consider a beam. What's a beam? Anybody? Yes, sir. What's, yeah, sure, a rigid body. That's one definition, but that's too general, isn't it? That's too general. I want something more specific, so any thoughts on what a beam is? You've seen beams in statics, right? You've done free body diagrams. We've been looking at free body diagrams for heaven knows how long. And you're tired of it by now, hopefully. What's a beam? No, not really. I mean, a two-force member could be a beam, but not all beams are two-force members. Anybody wants to hazard a guess?
Could this be a long body that's exposed to forces?
Beautiful, beautiful. It's just a long body, but you've got to qualify long. It is much longer in length compared to any of its cross-sectional dimensions. Absolutely fantastic. So that's a beam. Okay, so a beam. A human body I can treat, I'm not that tall, of course, but I can within, if you squint your eyes, I can treat myself as a beam. I'm much longer than I am in my circumference, though that's also growing larger these days. Okay, so a beam is any long body whose length is much larger than its cross-sectional dimensions. Much larger than any of its cross-sectional dimensions. Okay, so I'm going to consider a beam, just this long body. Okay, I have a support here. Some kind of a pin support. Let's say I have a roller at the other end. And let's say there is a force acting on this beam. (300 newtons). Distance from, let's call the support as A on one side. Let me call this as B, okay? And let's say that the distance from A to where the load is acting is 1 meter. And this one, not drawn to scale, of course, but it's half a meter. All of you still able to follow my writing on the board, people in the back, clearly? Okay. Right. Draw the shear force and bending moment. I'm also afraid that the board may fall on me. I'm I'm going to remove this entire panel here. Okay. And I just have one more request. Any one of you. Is it possible for one of you to take photos of my board work so that I can use it? Thank you very much. Thank you very much. Right? So that I can also post that on top of my videos, on my video. Okay, I do that for another class that I teach, and it kind of is effective. In some ways, it's almost like having your iPad notes, but after the class. Okay. All right. So how do I draw the shear force bending moment diagram? The first thing is I need to obtain the support reactions. Okay. So we draw the free body diagram. Support reaction at A and B. Sum of forces, sum of moments, and so on. First step. Obtain the support reactions. Draw the free body diagram. When you draw the free body diagram, you take this body, you wrench it from everything that holds it in place. I'm just going to draw it as a straight line, okay, if you don't mind. AY, BY. I have AX, but in reality AX is 0, right? There is no AX here. Just to complete my thought, I'll draw it out. And then I have the 300 Newton force. And distance from A to where the force is acting, from where the force is acting to B, 0.5 and 1 meter respectively. This is where your statics comes into play. And this is also where statics stops and then everything else begins. Right? So as some forces, as some moments. For some moments about the point B, please check out these calculations by doing it yourselves. I'm not going to do it. We have much better work to do here in this class, right? So I'm ending up with AY as the following. So 300 times 0.5 by 1.5, so 100 newtons. Sum of forces in the Y, and then AY is anyway 0, so we don't, AX is 0, we don't need to worry about it. I'm going to remove this panel if you all are okay with it. You take the photo. Okay. Yes, sir.
Wouldn't this be 150 newtons for AY?
Is AY 150? That's 300 times 0.5 and divided by 1.5.
Oh, okay.
Right. So 0.5 by 1.5 is 5 by 15, so that's 1 by 3. 300 by 3 is 100 newtons. Okay. All right. Okay, so now to draw the shear force and bending moment diagram, here is what I do. We've got to set up a coordinate frame. Okay, we've got to set up what is the positive x and positive y direction. So I start off this way. Here is my beam. I put back everything that I have calculated. Forget this guy AX because that's 0 anyways. AY was 100 newtons. Then I have the other force, VY. Newtons, and then the 300 Newton force, which you just then I mark the distances as well. And then I choose a coordinate system. Okay, this is where one has to be very careful. This is the way I solve these problems. I urge you to solve it the following way. My coordinate frame always starts from x is equal to 0 on the left and increases as I go to the right. Okay? So this is x is equal to 0. So this is my positive x direction, okay, pointing to the right. So this is x is equal to 0. Then if I come to the point where the load of 300 Newton is acting, that's x is equal to 1 meter. And as I go all the way to the end of the beam, this is x is equal to 1.5 meters. And my positive y direction is pointing up, as we expect it to be. I'm going to remove this pattern. So far so good, everybody? Okay. All right. So next step is this. I look at what are called as the loading discontinuities. Okay? So in some sense, this concentrated force is an anomaly, right? So we treat that as what is called as a loading discontinuity or a singularity because some special things are taking place at that location. Okay? Down or up or whatever. And if I have a bending couple moment acting on the body, that's also considered a point of loading discontinuity. We don't have it at this point in time, but we will be putting it back later in other problems. So between the first loading discontinuity and the second loading discontinuity, I take this beam and I slice it off at some location x. And I break the beam into two pieces. Remember your Kit Kat analogy. Break the beam into two pieces. But the value of my x is going to go from 0 meters and it's going to stop short of the 300 Newton force. Okay, so the value of x is going to go from 0 meters all the way up to 1 meter, not including the 1 meter location. So I'm going to draw that piece out here. You can either look at the right piece or the left piece, it does not make a difference to us. This is x. And in this situation, x goes from 0 to 1 meter. And on this particular piece, I put in all the elements of the loading and the internal forces and reactions that I see. Okay, so I start off with the support force here. AY is 100 newtons. I'm stopping short of this 300 Newton force, so this x is anywhere from here all the way right up to where the 300 Newton force acts. So in that region, what do I see? I see internal forces at some arbitrary location x. According to the sign convention, this is where you've got to be careful. According to the sign convention, I draw the internal resultant forces. Normal force. Don't have a normal force, obviously. It is drawn for completion. Shear. The direction of the shear force is such that it takes the cut piece and spins it clockwise. Okay? So this is the shear. And then the bending moment is such that it takes the cut piece and puts it in a concave upwards manner. This is where the bending moment becomes very important. This is the bending moment. Does this figure make sense to everyone? Any questions so far? Yes, sir.
Why do we go from 0 to 1 meters when you said like you're stopping before the 1 meter mark?
Right. So that's what the inequality here says.
Oh, listen. Okay.
So I'm not going up to 1 meter, but I'm stopping short of that. So choose two loading discontinuities. Start from the left side of the beam where x is equal to 0. Start from there. Go all the way up to where you have the first loading discontinuity. Right? This, in some sense, this is a support reaction, so it's not because of the loading, it's a consequence of the loading. Okay? It's not directly a load applied. Then I sum forces, I sum moments. In the x direction is equal to 0, the normal force is 0. We will ignore the normal force for the time being. So this is going to be the y direction, okay? Because I'm interested in shear and bending moment. Okay, so I'll just clarify it here. Choose a direction. AY is pointing up, V is pointing down. So 100. V is 100 newtons. We've done these things before, right, when we did internal forces and so on, so this is not hopefully new information for us. Then I do the bending moment. I have to sum the moments at any point along this cut. I do it at the cut, okay, so sum of moments at the cut. Counterclockwise moments are positive. So what do I see? First of all, M is a couple moment, so you just throw it into the mixture, okay? Capital M. Then the shear force is located at the cut. It does not contribute to the bending moment, and so I'm going to have this AY, right hand rule. Fingers of my right hand aligned with the force AY. My palm faces the cut. Curl my fingers into the bolt, which is counteractive to the sign convention that I've chosen. So this is minus AY times X. Or M is 100 times X. And you immediately recognize that between 0 meters and 1 meter, this guy is a constant value. Right? Because at any point I cut it, the shear force is going to be equal to 100 newtons. But between 0 meters and 1 meter, what is the magnitude of the bending moment? The bending moment starts at 0, when x is equal to 0, increases to 100 times 1, in what kind of a manner? A linear fashion. But 100 times x is a linear quantity. So you see that I really cannot just by inspection look at the problem and say, okay, hey, this is where the maximum bending moment is happening. I have to actually solve for it. Then I do the next cut. I stop short of this guy and now bring that person into consequence. I go all the way here and I cut somewhere in the middle. This is my second cut. And X is going to be the following. This is an X, but with some caveats. The caveat being, the value of my X is going to start at 1 meter and end at 1.5 meters. I'm going to draw it out. I'm first of all going to take this, break it into two pieces. I can either look at the small piece or the big piece. If this is X here, this distance here is the total length minus X, so 1.5 minus X. That's so many meters. And so if I draw the second piece, I'm going to draw it right down here. Newtons, okay. Length of this piece is 1.5 minus X, but be careful. The range of my X is now going to start at 1 meter and end at 1.5 meters. So here X 1 meter and ends at 1.5 meters. Okay, so less than or equal to, because that's the end of the problem anyways. Am I making sense to everybody? And And I draw the shear force and bending moments according to the sign convention. Because I'm cutting it from the left side, my shear force is going to be pointing up. Because it's going to take this cut piece and rotate it clockwise. Then I'm going to have my bending moment. Concave upwards according to the sign convention. Normal force if you want. Not very important for us. Right, so that's the second piece. Any questions so far? Yes, sir.
Why did we choose to include the 1 here but not the first piece?
Which one?
The 1 meter?
Because there is nothing else beyond there. Right? I mean, the loading ends at, if you want, you can just call it as less than 1.5, that's also fine. What we will see is that beyond 1.5, the beam is no longer there, so the shear force ends up being 0. But if there was a continuity here, if there was an extra segment to this where I had another loading pattern, then I would be stopping short at 1.5. Okay. All right. Any other questions before we proceed further?
Yes, outside of the beam in the inequality, you can include, you can say x is greater than or equal to 1 where the load is applied.
On this one?
For the other one.
Oh yes, absolutely. Now here is where we start at x is equal to 1, and then we go all the way to 1.5. Okay. Towards the end of this beam in this situation, because that's where my last load is present. But if the beam were to continue, then I would have to do one more piece probably. Yes, sir.
So how come we're not including the 300 Newton force then?
Well, I could include it if I'm looking at the other side of the cut. So as I said, you can take any beam, if you're making a cut, break it into 2 pieces. You could analyze either the small piece or the big piece. The answer is going to be the same. So this is equivalent to analyzing the following. Okay, so just to, it will give you the same answer if I did the following as well. If I say this is 100. This is 300 newtons. And this is total distance x, where my x is once again in the range from 1 to 1.5. And I can draw my shear forces and so on. It's the same thing, absolutely the same thing. So you can either look at the small piece or the big piece. Yes, sir.
I think it's important to remember, and it's something that helps me understand that, is like we don't have to necessarily take the 300 into account because remember we found the reaction forces.
Yeah.
Based on 300.
Then you can also say that, yeah, right. This is a consequence of the reaction force. Absolutely, absolutely. Very nice. Very nice. Yep. Okay. Does this make sense to everybody? So I can either look at one piece or the other piece. Why is that? Is because every body in statics and mechanics of materials is a rigid body in static equilibrium. So you either look at one side or the other side, the answer is going to end up being the same. Yes, sir.
Could you say the bar is in compression, like
Could I say the bar is in compression?
from the force?
No, so compression or tension is defined in the axial direction.
Okay.
Right, so in this case, what you are essentially saying is that because of, so you imagine it this way, there is a pin here, there is a roller here, I'm pushing the bar in the middle, it's going to start bending. Right, you see that?
Yeah, because it's opposite.
Right. And so this is essentially trying to push it down, the supports are trying to prevent it from going anywhere, so it's going to have, in reality, a deflection at the middle of the beam or wherever the load is acting. And the deflection magnitude is going to keep reducing as I go to the end of the beam because the end of the beams are fixed. Yes, sir.
Is there such a quantity as transverse compression where it's along the cross section? Or
That's
it's not axial?
So that the transverse compression that you talk about is an effect of the shear force.
Okay.
And so that's a shear stress.
Okay.
Absolutely. So the shear stress is spread out all through the cross section.
Okay.
Yeah. Fantastic. Any other questions, please? Are you all enjoying chalkboard as opposed to writing on the iPad? Yes.
I just want to say that your handwriting is really good.
Thank you. Appreciate it. I like kind words too. All right, thank you. we'll continue. So I need to do the sum of the forces and the sum of the moments as well. So for the second piece, with your permission, I'm going to discard this panel here. Okay? Sure, absolutely. Yeah. Okay, so sum of forces, sum of moments. Second cut. Next time, maybe if I'm doing this on Friday, I'll bring some colored chalk as well, so that we can draw different pieces using different colors. We'll try to come close to notability as much as we can. So sum of forces. And I feel this is also more interactive in some sense. I'm seeing more questions than the typical class. And what really, in some sense, pisses me off is, I'm standing here at the iPad, looking down. The entire room is dark, and puts me in a really dark mood. But it's just saying. Okay, so sum of forces in the y direction, I'm going to have the force V, 200 newtons. Now you immediately notice that this has to be negative to counter the effect of the 200 Newton force. Okay, so this is V plus 200 Newton is equal to 0 because both the forces are pointing up. So I'm going to have V is minus 200 Newtons. Sum of moments. I always sum moments about the cut. Okay. And if I do that, first thing is I put the couple moment M. Now notice this. This is a generic sign convention. I'm just saying clockwise moments are positive. This sign convention is a sacred sign convention. Because this says that concave upwards is positive from the perspective of bending stresses. There are two different things. We don't want to conflate the two. This is just for convenience. This is sacred. Don't mess with that. You can change this any day you want. I can come tomorrow and say clockwise moments are positive and I sum moments up. Okay? It doesn't change anything to me. I'm going to have minus M because M is drawn clockwise. In this case, I'm saying counterclockwise is positive. And then right hand rule. Fingers of my right hand aligned with the 200 Newton force. My palm is facing the cut section. Curl my fingers, comes out of the board, so positive. 200 times 1.5 minus x is equal to 0. So, M is and you agree with me, this is laborious. I'm cutting it here, cutting it there, doing some forces, some moments, what the hell, right? Okay, but I'll show you what we are eventually going to get from all of this. Keep in mind, the first cut, 100x, what's the slope of this curve? 100, positive. If I come here, what's the slope of this curve? Negative 200. So I'm starting up climbing as I go from the beginning of the beam for the bending moment. Then as I come towards the end of the beam, the bending moment is climbing down again. Okay, so it's a positive slope, it's a negative slope. They reach a maxima at some point. Okay? So what I want to do is I want to collect all my results here. And is it okay if I erase this? Yes, please.
If your dust slope is positive, dust slope is negative, in the mornings, how will that affect our moment of inertia?
Moment of inertia is not due to the moment of a body, moment acting on a body. Moment of inertia is a geometric property. Right. So that's dependent on the cross section that you have. That has nothing to do with the loading that you provide. But when you design structures, for an optimum performance, right? So what you optimize typically in mechanics of materials is you want to optimize it so that the moment of inertia is kind of minimized. Yes?
Are those M's the same?
No, they're different. They're for different pieces. So maybe let's call this as moment M1, let's say. This is M1. This is M2. M2. V2. V1. Yep. Okay. So I'm going to get rid of this panel here and write down all my results so far. Okay, so from 0 to 1. V was I think we called it as V1. Right, so M1 was 100. And then from 1 to 1.5. V2 minus 200, we just obtained that value, and M2 has a negative slope. Is times 1.5 minus x. How did I find the slope? The slope is dm by dx. Okay, so slope this is the slope for the bending moment diagram. Okay. And the dV by dx is the slope for the shear force diagram. Okay. Yes, sir.
You may answer this very soon, but intuitively I want to say that because you increase x, the shear force implies a greater torque and therefore a greater bending moment. Is that fair to say, like if I were to look at that beam? And I was just wondering, like if you differentiate that, does that make the moment independent of the location x?
Not really. It just tells me how the moment value is falling down as a function of x or increasing as a function of x. Right. That's what the slope tells me. So for example, if I look at dV by dx, right, V is 100 newtons, V2 is 200 newtons
Oh,
minus.
yeah, I understand that. I was,
Right.
The moment's not changing. Okay, I see.
Right. The magnitude of the moment is reducing or increasing, yeah, depending on it. So just to clarify what's going on is, this tells me qualitatively how the moment is changing as a function of the position x along the length of the beam. Okay? And nicely seeing here, dV by dx, if I take dV by dx here, what do I get? 0, which tells you that the shear force is a constant all through that piece. And likewise, if I take a dV by dx here, this is also 0 because it's a constant value, so the shear force is going to be constant along that piece. Okay? And bending stresses, shear stresses and bending stresses, in my opinion, are very closely related to geometry. And this is where a lot of geometric, graphical aspects of the problem comes into play. Yes, sir.
Did you arbitrarily pick for the intervals to have the 1 meter included in the second interval?
No. So all I'm saying is that when let me go back to the beam. What I'm saying is that, let's say that I start here. What's the bending moment there? 0, right? Because there is no beam present, there is no shear force also present, shear force also 0. Then I immediately say that as soon as I pass this guy, but as long as I stop short of this guy, I see that there is a different characteristic for the shear force, which is a constant value of 100 newtons. And then I'm saying that, okay, now let me include the effect of this, the direction of the shear force changes and the magnitude also changes. So what I'm doing is, I'm looking at this beam and I'm seeing there are these events taking place. There is an event taking place here, there is something going on here, there is something going on here. And what I want to capture is the evolution of the shear force and the bending moment as a function of the distance. And as a function of these events also.
So, but was there a reason you included it in the second?
Because I did not include it in the first.
Okay, so it's just like,
Right. Because you don't want to feel left out,
Okay.
in some sense. Right. Figuratively speaking as well, right? Yeah. Yes, you had questions.
Yeah, I was just gonna kind of build on that. So you could have included the 300 Newton in the first interval and not in the second, just as long as it's included in one of them?
Not really, because if I included it in the first one, right, then I would have to cut it here. That is right after the 300 newtons, which will tell me that the value of the shear force is minus 200 newtons. And I will lose out the information that is given here, in this piece. Does this make sense? So, you can think of it this way. Let's say, I make a cut here, okay? If I make a cut there, you see that the value of my shear force is 100 newtons, right? Instead of making a cut there, I rather made the cut here. What I would see is that the magnitude of my shear force is not going to be 100 newtons, but it's going to be 300 newtons minus 100, so 200 newtons. And in effect, what I'm doing is I'm skipping over all the changes that are taking place in this piece. So which is why I'm saying we are going to limit ourselves to looking at two loading events, or two loading discontinuities. So here is the first discontinuity, here is the second one, here is the third one. Your first cut is going to be between this and that, not including that. Your second cut is going to be between here and there, now include the effect of this one. In reality, I should not be including this as well. I should be doing the same thing as the previous case, but the beam is ending there anyways. So there's nothing more to see after that. Does this make sense? Alright, very nice questions. Okay, I'm going to remove this panel here so that we can draw our figures. Okay. Alright, so now I'm going to draw the shear force diagram. This is x, which is distance along the length of the beam. Okay, here is the shear force value. This is 0. Any questions, please? Okay, we'll move on. I marked the locations along the beam where we had the loading discontinuities taking place. So this is 0 meters, 1 meter, 1.5 meters, and then right below that I'm going to draw what I call as a bending moment diagram. Separate figure. We have not drawn the figures, of course. I'm just drawing these axes. Things that I want to see in your work. I want to see the axes labeled with the dimensions. I want to see the axes on the vertical directions also labeled with their dimensions. So this is newtons. This is Newton meters. All right, you're all ready for this now? Start off at x is equal to 0, and I go all the way up till this 1 meter. What is the value of the shear force? The value of the shear force is a constant plus 100 newtons. Okay, so I just mark off some 100 newtons here. That's 100. I'm sorry if my writing is not legible to people in the back. Okay, so that's 100 newtons. I start off there and I say that every point between 0 and 1 meter, the value of the bending at the shear force is a constant 100 newtons. I just draw it out this way. Immediately I come to this location of 1 meter and beyond. What do I see?
It's not negative, so.
Absolutely. I see that the value of the bending shear force has gone down to 200 Newton meters in a negative direction. So mark out minus 200 newtons there. Pull this curve down to that value. Okay. And then as I go from 1 meter to 1.5 meters, what's the value of the shear force? The shear force stays constant at minus 200 newtons all the way down. And then right after 1.5 meters, what's the shear force value? It's 0 because there is no more of the beam left. So I come back to 0. I always come back home. Okay, home is 0. Yes, sir.
Is it necessary at x equals 0 to also have a vertical line that goes up to 100?
Absolutely, absolutely, absolutely. Yes, fantastic. Yeah. So there is this piece. And there is that piece. And immediately it tells me, okay, so this is first of all the shear force diagram. These are the regions in the shear force diagram. There is one region that's consistently constant as 100 newtons. There is another region which is consistently negative as minus 200 newtons. My question to all of you, what is the maximum value of the shear force?
Talk about magnitude or?
I'm going to answer, tell only the question. I'm not going to specify magnitude or signs. What is, and I mentioned this specifically in a previous lecture.
200 newtons.
The maximum value of the shear force is 200 newtons with a negative sign. The negative sign tells me that if I, and I'm going to talk about this in the next class, the negative sign tells me that if I cut the beam at that location, the shear force is going to be pointing opposite to the sign convention. That's what the negative sign tells me. Okay? Then I do the bending moment quickly. 100 times x from 0 to 1. X is equal to 0, bending moment is 0. X is equal to 1 or close to 1. 100 newtons, close to 100 newtons, meters. Increases in a linear fashion. Interestingly enough, if I substitute x is equal to 1 meter here, what's the value of the bending moment? It's also 100. So there is continuity there. Once again, this guy was from 0 to 1 meter, stopping short of the 1 meter, right? So which means that my bending moment started at 0, increases linearly to probably close to 100 Newton meters, right? At x is equal to 1 meter, if I substitute x is equal to 1 here, I get 100 Newton meters, which I should not be doing because this is stopping short of 1 meter. But then the other piece is going to take over from there. If I substitute x is equal to 1, 1.5 minus 1 is 0.5. 0.5 times 200 is 100 Newton meters. So there is continuity at that point. And if I substitute x is equal to 1.5 for the second piece, I end up getting 0 Newton meters. So I fall down like a ton of bricks. Okay, so this is my bending moment diagram. So V max is minus 200 newtons. That negative sign is important. It tells you that you're doing things against the sign convention. M max, obviously, is 100 Newton meters positive, which tells you that you are in accordance with the sign convention if I slice it at that particular location on the beam. Do you all see what I'm seeing here? At the point where the shear force crosses the x-axis, there is a special event taking place in the bending moment diagram. which tells me that the integral of the shear force diagram is the bending moment diagram. And that is the geometric perspective that you want to have offer in this kind of a problem. So, and we are going to do this in the graphical technique on Friday. It's all going to be only integrals and differentials. But one thing I want to say is, as there is a crossover taking place, there is a maxima or a minima reached. It could be a minima as well, depending on the problem. It could be something flipped over onto the bottom side. This guy is the integral of that. That's essentially what it is. And dm by dx is nothing but the value of the shear force. If I do dm by dx in the first one, it's 100. That's the value of the shear force. If I do dm by dx in the second one, it's minus 200. That's the value of the shear force here. Okay? Thank you for your time and patience. See you all on Friday. Is there
Será que